Okay, so let's begin with an example. So two particles are in SHM along parallel lines with identical amplitude So at time t equal to 0, they are at so find the earliest time at which their x coordinates coincide. Write the equation of SHM for each. So this is a question again based on the kinematics of simple harmonic motion. Just try this out, we'll discuss. Okay, so let's say we write the equations for particle 1 and particle 2 separately. So for particle 1, the initial position is, so that is, and the velocity is negative. For particle 2, the initial position is minus 2 millimeters or minus a by 2, and the velocity is also negative. So what will be the phase constant for this one? What will be the phase constant for this one? They both have amplitude equal to 4 millimeter.
First, we need to find omega.
Yeah, omega also you need to find out, but phase constant also, no? So omega to ठीक है 2 pi upon time period, right? So how much that's becoming? Pi by 6 radians per millisecond. So if you want to convert this to SI unit, it will become like this. So this is common for both of them, this information. But to find out when they cross each other or when their x coordinates coincide, you also need to know their phase constants. That is the only difference in their equation of SHM, the phase constant. Otherwise, both have common amplitude and common time period. You're understanding the point, no?
Sir,
Yes.
sir, how come both of them will have negative velocity?
Sorry, come again.
सर वो लोग coincide कर रहे हैं, सर एक जो आगे का डायरेक्शन में जाएगा दूसरे पीछे आएगा कि ऐसा नहीं है, दोनों सेम डायरेक्शन में जा रहे हैं.
हाँ, दोनों सेम डायरेक्शन में जा रहे हैं along the negative x-axis. So you visualize it like this, na? Let's say these are the tracks, the parallel tracks along which the SHM is happening. This one and this one. Okay. So this is between plus A and minus A. So this is the common origin for both of them. Okay. Now at t equal to 0, the first one is here and it's moving like this. And at the same instant, this one is here and it's moving like this. You're understanding no? Now?
Okay.
Okay. So क्या होगा? This one is, after this it will be here and like this. This one will be here and like this. So at some point of time they'll cross each other. No? That is when for the first time their x coordinates coincide.
Okay.
So they are both doing SHMs parallelly. So they are moving like this. So they are crossing each other periodically. Okay, so it is all about finding the phase constant for each one and using the equation of SHM to find out when the x coordinate of the first is equal to the x coordinate of the second. Now this is also a type of problem where your visualization of SHM by projection of uniform circular motion that can make the problem very fast. I mean, can make the solving of the problem very fast. So you can get the phase constant by using that also. Just try this out. Okay, so for the first one, you will see that the phase constant is equal to 5 pi by 6. Okay. And for the second one, the phase constant is equal to 7 pi by 6. Okay, because for this one, like that is if you take the equation as A sine omega t plus 5. Because sine phi 1 has to be plus half, but cos phi 1 has to be negative. And here sine phi 1 is minus half, cos phi 1 is also minus negative. Okay. So we have the two equations. Okay, so therefore their x coordinates coincide when x1 is equal to x2 Okay, so we have to solve this equation trigonometrically now. Okay. So this is where trigonometrically this becomes a little challenging. But if you just okay, so first of all, hope the phase constant is clear to all of you. The values of the phase constant. Okay, so this is a bit like solving something like this now. Let's take omega t plus 5 pi by 6 as alpha. So omega t plus 7 pi by 6 can be written as alpha plus pi by 3. So if you're solving something like this, that sine alpha is equal to sine of alpha plus pi by 3. So that means alpha plus pi by 3 should be equal to, in general, 2n plus 1 pi minus alpha. This is the general solution. Okay, we are using this concept that if sine alpha is equal to sine of alpha plus pi by 3. Okay. Now you know that sine of pi minus theta is equal to sine theta. Sine of 3 pi minus theta is equal to sine theta. Sine of 5 pi minus theta is equal to sine theta. Like that in general. So using this identity, you can see that if this value is in general 2n plus 1 pi minus of this value, then you understood now? So 2 pi upon time period into t should be in general equal to, so this will just become like n pi plus pi by 2 minus pi. So that's the same thing as when n is any integer value. So n minus 1 is the same thing as, so the time will be like n minus 1 times p by 2 plus p by 4. So it's these series of times. So yeah, as I told you, like trigonometrically, it's a little tricky solving something like this. So that is where, if you look at SHM as a projection of UCM, this becomes a somewhat simpler sum to solve. Now going back to that visualization of this on the linear axis like this. Initially, they were like this, no? This was what was happening at t equal to 0. Okay. So what will happen after t by 4 amount of time? Okay. So the first one at t equal to t by 4, x1 will be how much? It will be a sine omega into t by 4 plus 5 pi by 6. So that will be a sine pi by 2 plus pi by 6. So it will be at and the second one plus 5 pi by 6. So, you know, by the time this has reached here directly, it's moving in this direction, this one has actually gone like this and come back, and it's here. So their positions coincide at minus root 3 by 2. So this is the visualization of it on the linear graph, I mean on the linear paths. Okay. So it's very difficult to directly calculate this the way I've done here. So that is where the projection of UCM method comes in. Okay. By projection of uniform circular motion method.
So you just compare the position in the UCM path.
Yeah, that's what we do. So just imagine the vertical one here is the SHM axis actually, because we are used to writing it in the form of sine. So we'll take this as our x-axis only. Now at t equal to 0, the first particle is where it's at a by 2 and moving along the negative direction. So the first particle's projection should be at a by 2, but its direction should be downwards. So if omega is like this, that means the first particle is here. So this is where our particle 1 is at t equal to 0. And our second particle is at minus a by 2 and also moving downwards. So our second particle is here. At t equal to 0. In fact, if you draw this, this will be a vertical line over here properly. Okay. Now see what is going to happen, because they have a common value of omega now. As they are rotating, I mean, as you visualize the uniform circular motion of the two particles, you'll realize that the line joining them always remains the same chord. It's just the position of that chord that changes. Because both these particles are moving with the same omega. No? So initially, they're like this. But for example, after some time, if this one has come here, this one would have come here. Like this. Okay. Then after some time, if this one has come here, this one has come here. So they'll always be like this. Okay. So
distance same होगा दोनों के बीच में.
Sorry, come again, beta.
Distance between them, the chord will be always
that it's like it's a fixed chord. It's a fixed chord which is rotating like this. So now you can see that the first time their x coordinates become common, what should happen? X is, remember, the vertical over here. So the first time their x coordinates become common, what should happen? This chord should become horizontal.
horizontal.
Yes, sir.
Okay. So they should.
So what is on the x-axis?
Sir, पर horizontal भी दो जगह होगा ना sir?
X is, see, if you take the radius of this as a, na, x is a sine omega t plus phi, na? That is the general solution. You understanding, na? What is on the x-axis?
Can you repeat once?
The projection on the x-axis only is the SHM. No? Right? We had discussed last time, no, that uniform circular motion, if a particle is located here at some time, where this angle is how much? This angle is omega t plus phi, na, in general, if phi is the initial angle. So what is this projection? It is a sine theta, na? So it is a sine omega t plus phi.
Yes, sir. Understood.
Remember this, no? Okay.
Yes.
Okay. So now see also
Sir,
because yeah,
sir, you said that their position, that x coordinate will be equal when the line that chord is horizontal, but that will be at two positions, right?
yeah. So it keeps happening periodically, no? It's not just one time.
Okay, okay.
The earliest time, see, they are going like this. So what is the earliest time? This is t equal to 0 picture. What is the earliest time when you see this, their x coordinates becoming the same? When it becomes like this, no? With
Yes, sir.
some negative value, no? So that will be the earliest time when. So if we compare this diagram now to this one,
Yes, sir.
where this has happened, okay. So their position has become something like this.
Yes, sir.
So this is where particle 2 is located, and this is where particle 1 is located. Okay, so their projections will actually be crossing each other. Now you can see it's a chord of fixed length, no? And in fact, this is very easy. This is 30 plus 30, 60. So there's actually an equilateral triangle. Okay, so this position will be when this is 30 and this is 30.
Yes, sir.
Okay, so now we can see what is the angle. So this is some time t1, let's say. Now this is very easy to find this time because where did particle 1 start from? Particle 1 started from here. This was at t equal to 0. Okay. So how much
So
particle 1
that
is
was
traveling?
y by 50.
You can see the angular displacement, that is omega t1 is equal to how much? It is pi by 6 plus pi by 3 for both of them. So it's 90 degrees, no? And
Yes.
90 degrees always equivalents to quarter of the time period.
Yes, sir.
Okay. Similarly, this one also has gone from this position where this was pi by 6 to this position. So it has traveled pi by 3 plus pi by 6 like this. No?
Yes.
Yes, sir.
So this gives you like a solution immediately. Now the next time when their positions coincide will be when this becomes
That will be
vertically.
yes.
So
Again
that will
90.
be exactly 90-degree displacement again. Okay. So that will be the next time. So
Sir.
that at that point of time, P1 has reached here and P2 has reached here. So if this time is T2, you will see that T2 is equal to T1 plus T by 4.
Yes, sir.
Like that. So that is the series we have got getting above also. No? Let's see. T by 4 plus T by 4, sorry, plus T by 2 over here, because this is, they are
Yes.
going by 180 degrees. So this is like pi by 4, so T by 2.
T by 2.
So then the third time will become like that. T2 plus T by 2 like that. So that series becomes like this. Three T by 4. 5T by 4 and like that.
Yes, sir.
Okay, so this is the for particularly this type of questions in JEE Advanced. You have to be familiar with that, using that method of projection of UCM being an SHM, because otherwise trigonometrically you can see how difficult the problem is.
Sir.
You have to solve this thing, which is very difficult. Even the phase constant to begin with is a big job finding phi1 and phi2, whereas here you can directly visualize it now, so it becomes very simple. Okay.
Sir,
Yes.
जो particle 2 का जो can you go up?
Yeah. Yeah. Phi2.
So phi 2 में sir that will be negative, cos be negative, sin be negative. Okay.
Why? Because see, it is given to us that V0 is negative for both of them.
Okay.
And the particle 2's position is minus a by 2. So
Okay.
it is sine inverse of minus half, such that cos is also negative.
Okay, sir. Third quadrant.
Yeah, Jagannath, how we got T1 as T by 4 actually. How we got T1 as T by 4 is because see, this angular displacement omega T1, this is pi by 2. You understood this, no? as this plus t by 2. Okay. So see in the second diagram, how the particles are moving. They are going from this position at T1. P1 was here, P2 was here. So this was pi by 6 now. So in the second diagram at T2, this is pi by 6. So this particle is going diametrically opposite now. This particle is going diametrically opposite now. So this angular displacement from here to here, it is actually what omega into the time now. Omega into delta t. So omega into T2 minus T1 is pi. Okay, so that's how we are getting T2 minus T1 is capital T by 2.
Okay.
So, just get used to this method of, first of all, just visualizing this, that this particle is going round and round in this. So its shadow on this axis is that A sine omega t plus phi 1. Okay, if you took its shadow on the horizontal axis, it would be the E cos omega t plus. So you can solve the problem that way also. Okay, but we are used to taking sine, so we are taking the vertical one. And once you are used to that, then you can see it's very easy to use the properties of the circle rather than use sine and cos, just technically a little bit more difficult. Okay, so this is about like the maximum level of difficulty in kinematics of SHM type of problems you can get. Now back to SHM of spring mass systems, which we were discussing last time. So dynamics, yeah, I'll go back. Yeah, which part? This one? Okay. Okay, done with this, Jagannath. Okay. Okay, so now let's move on to back to dynamics and spring mass systems. So last time we had seen the basic spring mass system. To start with, single spring attached to a block on a horizontal plane. So if let's say at t equal to 0, the situation was such that the position of the spring was at some extension of x naught, okay, and the block was moving with a velocity v naught like this. Then at some general time t, let's say change to this. V would be like this or coming back or whatever. Okay. So we already have this relation that t is equal to ma, so kx is equal to ma. So a, which is minus d2x by dt square, becomes k by mx. So we have our
Yes.
equation of SHM here. So from that we see that omega is square root of k by m. Time period is 2 pi under root m by k. And also from the initial picture, we are able to calculate the amplitude and the phase constant. Okay, so this tells me that x is some a sine omega t plus phi. V is a omega cos omega t plus phi. So from this, my x naught is a sine phi. This my v naught is a omega cos phi. So now using this set of equations, we know that a is equal to square root of x naught square plus v naught square by omega square, and phi is tan inverse of x naught divided by v naught by omega. So we get all these things. Okay. So as long as we know the value of the spring constant, the mass of the block, so from the physical properties, that is k and m, we get omega. Time period, frequency are determined. And then from the initial condition of the system. So by initial condition, we mean what is the initial displacement and initial velocity. We determine the amplitude and phase constant. So that gives us the equation of SHM. So this was the general idea. Okay. Now we will also see the application of work energy and mechanical energy of oscillation next.
So for that phase constant formula, what have you written?
Tan inverse of x naught omega by v naught. Okay. So that remember comes by dividing these two equations. If you divide this equation by this equation, you'll get x naught by v naught is 1 by omega tan phi, right?
Yes, sir.
Okay. So you don't need to
Yes.
separately memorize these formula also. Just remember that everything comes by logic from these two equations only. Okay, so this is clear now.
Sir, 1
Okay,
minute.
now yeah.
Sir, in phase constant, that is tan inverse.
Yes, that comes by dividing these two equations. Tan phi will come out to be x naught by v naught divided by omega. So that omega comes in the numerator.
Yes, sir. Sir, what you have written about from physical properties about that? Na?
Note. Just a
Note.
note.
Done, sir.
Okay. So quick example of this. Okay. So suppose we have a system which has spring constant equal to, let us say, 4 newtons per centimeter attached to a block of mass 1 kg. Now, initially, suppose the system is at the natural length position of the spring, okay, at t equal to 0. And what we do to set up the motion is we apply a sharp impulse, like a collision impulse. So a sharp impulse of j is equal to, let us say, 0.2 Newton second is applied at t equal to 0. Okay. So find the time period, frequency, and amplitude of the resulting SHM and write its equation. So when you write its equation, the phase constant will also become important. So when I'm saying write its equation, write x as a function of time, where x is the extension of the spring. Because when the block is to the right of the mean position, the spring is extended, and when it's to the left, the spring is compressed. So taking this as our x-axis and this mean position as x equal to 0. So naturally, the x coordinate of the block as a function of time is the same thing as the extension of the spring. Okay, so what will be the velocity of the block just after the application of the impulse? As the motion starts just after t equal to 0, so we can say 0 plus. We'll have a velocity in this direction, but x naught will be 0 because it's starting from the natural length position, right? So just after the impulse is applied, with proper sign convention, the velocity of the block is this much, no? So it is minus 2 meters per second or minus 20 centimeters per second, and x naught is equal to 0. So this is your initial condition. V naught is negative and x naught is 0. So what kind of amplitude and phase constant? Okay. Now the other thing is standard formula, omega square is k by m. So that is 4 into 10 raised power 2 Newton per meter divided by mass, which is 1 kg. So omega is 20 radians per second. So time period is pi by 10 seconds. Frequency is 10 by pi hertz. Something like 3.2 hertz. So now we know omega, we know x naught and v naught. So we can see that the amplitude is just one centimeter is the amplitude. Because x naught is 0 and v naught is minus 0.2, but you're squaring it, so it makes no difference. Okay. So that's this. And phase constant is going to be how much? It's tan inverse 0, but such that cos phi is negative because v naught is negative. So it should be pi. The phase constant is 5, the amplitude is this much. So the equation of SHM will become 1 centimeter sine of 20 pi, sorry, 20 t plus pi. So that is the same thing as minus sine 20 t. So this is x as a function of time, where x is in centimeters, t is in seconds. Okay, so this is the direct application, how you should be able to do. Just using the standard formulae for the standard spring mass system. You don't have to go into any of the derivations or fundamentals like that. You just remember these two things, that omega depends on the properties of the system, that is K and M. So it has nothing to do with the starting conditions, but it just depends on the physical properties, the stiffness of the spring, the mass of the block. But on the other hand, the amplitude and phase constant, they depend on the initial conditions. So V naught and X naught's value tells you how far it will go, that is the amplitude, and also the starting position, that is what is the phase constant, initial phase of SHM. Okay, so this is clear. Anybody has a doubt with this? Okay. Now, okay, Jagannath, I'll wait.
Sir,
Yes.
how did you get sine phi is equal to 0 at the end?
How did we get sine phi is equal to 0 at the end? Because see what is happening, your starting position is x naught is equal to 0, no?
Yes,
So
sir.
x naught क्या होता है? A sin phi होता है ना?
Yes, sir.
Okay, done.
Yes.
Okay, very good. Yes, Jagannath. Okay, so let's move on. Now the next thing is mechanical energy of oscillation. Or rather we should say mechanical energy of SHM. So one is we can understand this in context of the basic spring mass system first, and then we can generalize it. So for example, spring mass system. So now at any general time t, whether the spring is extended or compressed, I'll just take the case where let's say it's having an extension of x and the block could be moving in either direction, it doesn't matter. So at some time t, this is happening.
Spring mass you have written.
Sorry?
At spring mass you have written, no?
Yeah, spring mass system. Okay. So potential energy of the spring is half kx square.
Yes, sir.
So potential energy as a function of time will become half k a square sine square omega t plus 5, because our x is and omega is square root k by m. So keeping all these things in mind, our kinetic energy is half mv square. So as a function of time, kinetic energy becomes so one thing you can see is that if you take the total mechanical energy as the sum of potential plus kinetic energy, it's easy to understand that it's equal to this much, because in this term, omega square, m omega square is the same thing as k. So this is again half ka square cos square. This should be a cos square. Yeah. Cos square omega t plus phi, because m omega square is equal to k. Okay. So now if you sum these two, sine square plus cos square is 1. So we get the very important property that the total mechanical energy is proportional to square of the amplitude. Also, the potential energy is half kx square. The kinetic energy can be expressed as half k into a square minus x square. So this is kinetic energy as a function of x. So this we can do basically by taking cos square omega t plus phi as 1 minus sine square omega t plus phi. So this is one way of understanding it. So if you also look at this graphically, in terms of position, look at energy. So the potential energy function the potential energy function is parabolic like this. The kinetic energy function is parabolic like this. And that is why the sum will be constant. Total mechanical energy is constant.
Sir,
Yes.
sir, will this graph be parabolic for like only as a spring mass system ka SHM ya all the SHMs possible?
It will be for all SHMs, and we'll do the proof of that in a bit. But
Okay.
like right now, just take it from the example of this simple spring mass system, a horizontal spring mass system.
Okay, sir.
So for example, if we have a vertical spring mass system, then the way we express the potential energy will be a little different, because it will be the sum of gravitational potential energy and spring's potential energy. But again, it will ultimately come out to be a similar kind of expression. It will be, quadratic. Okay, so let's understand this in general. Before that, let's also look at the graph of potential and kinetic energy as a function of time. We've looked at the graphical representation with respect to position, or with respect to time if we look at energy. So let's take the simple example of x is equal to a sine omega t. Take the phase constant as 0. So v becomes a omega cos omega t. So you can see that potential energy is half k a square sine square omega t function, whereas kinetic energy is half m a square omega square cos square omega t. So we'll plot these two. So our potential energy will become that sine square graph. So in one cycle, the potential energy goes between 0 and maximum twice. And at the same time, the kinetic energy will be like the cos square graph.
सर तो इसको इनडायरेक्टली स्प्रिंग का ग्राफ बोल सकते हैं ना?
Yeah, this we are still plotting the spring mass system graph only.
हाँ.
So this is our kinetic energy. And the total mechanical energy is constant. Okay, so for example, we have something like this, that a spring mass system of spring constant, just for simplicity, let's take the same value. Amplitude, let's take 2 millimeter. Okay. Starts from a position such that kinetic energy is equal to potential energy at t equal to 0, and x naught is positive, b naught is positive. So find mechanical energy of the system, omega, time period and frequency, and third, write x as a function of time.
So the Newton per meter, Newton per centimeter.
Newton per centimeter. Yeah, so very good. So let's look at the answers quickly. So you start by understanding that total mechanical energy is half K square. Okay. In SI unit, this is this much, and amplitude is this much. Okay, Piyush, got this now? Is the same value as the last question we did. So Piyush, I think you have taken the value of K in Newton per meter, but it is in Newton per centimeter. Huh?
sir. No, sir, I converted the values, sir.
Okay.
सर I actually forgot I had to take square ना इसलिए वो into
Okay.
को हाँ इसलिए मेरा गलत आ रहा है.
Okay. Okay. Okay, now the only tricky part of the question, writing x as a function of time. So for that we need x naught and v naught. Okay. So they are both positive, we know. So phi will be a acute angle. But what else we know? That initially it starts from a position at which the kinetic energy is equal to the potential energy. So this should give us a hint, okay, about the phase constant. If kinetic energy is equal to potential energy, what can we say about x naught and v naught? Okay, so at t equal to 0, kinetic energy is equal to potential energy. That means half k a square minus x naught square is equal to half k x naught square. Okay. So x naught square is equal to a square by 2. So x naught in general is plus minus a by root 2. But here it is also given that x naught is positive and v naught is positive. So that will explain what will happen. Okay. So that means sine phi, given this that is positive and its value is this, is 1 by root 2, and cos phi is also positive. So the phase constant is how much? It is pi by 4 or 45 degrees.
Yes, sir.
Equation of SHM will become amplitude was given to us. Okay. Omega we calculated. And now most importantly, phase constant is pi by 4.
Yes, sir.
कितना था 2 millimeters. Okay, so this question is clear. I hope all the aspects. Okay. Now we'll come back to that energy in general also, how we can prove that it will always be of that type. Okay, that kinetic energy will be proportional to a square minus x square in any SHM, not just spring mass system, and potential energy will be proportional to x square. But currently we'll move on to, so we'll come back to that general expression, but currently we'll move on to vertical spring mass system. So the basic template of the vertical spring mass system is, imagine we have a block attached to a spring suspended vertically, and the spring is ideal, so it is massless. So first of all, we want to show that the system will perform SHM vertically if disturbed from the equilibrium. Again, vertically disturbed. If you give it some random kind of disturbance, then it will have a very random motion. If you just give it some vertical displacement by either applying a vertical impulse or giving some initial displacement vertically, then it will perform SHM in the vertical direction and find time period of SHM. Okay. So the condition for SHM we know is always that d2x by dt square is equal to minus omega square x. That kind of equation we should be getting. But here what we'll have to do is we'll have to adapt that equation a little, because x is the displacement from mean position. So here that x is not going to be the same as the extension of the spring. So we will use a notation here where the position or displacement we will write as the variable y, whereas the extension of the spring we will use the variable x for it. Okay, so we'll use separate variables. So this is the SHM variable, and therefore we should take y equal to 0 as the mean position or the equilibrium position. Okay. So we will accordingly calibrate our system. Okay, so let's say this is our mean position. So this is the stable equilibrium position. Acceleration should be 0. So at this position, let us say the extension of the spring is x0. So accordingly, this should be our y equal to 0 position also. So from the free body diagram, we can understand that mg is equal to kx0 at the mean position. Okay. So x0 is equal to mg by k. Now from this position, if we take it to a vertical displacement, then we should be able to prove that whichever direction we take the vertical displacement in, it is going to give us an SHM. Okay, so just going to draw that like this. So now imagine from here, if I've taken it to a position where it is here, let's say. Okay. So if this was a y equal to 0 position, then here it has been given some positive y, or we take it to a position like this below. So it has been given some negative y, because we are taking this as our y-axis, this point as a y equal to 0. Given some negative y. So here, the extension of the spring in this case would have become x0 minus y. And if y is greater than x0, then it's actually compressed. Okay. So we will see it will have a downward acceleration because mg is dominating. And in this diagram, we'll see the extension of the spring has become x0 again minus of y, but y is a negative quantity. So x is greater than x0. So it will have an upward acceleration. So whichever diagram we go with, the first one or the second one, you can see that in general, for the first diagram, we have mg minus k of x0 minus y is equal to m. So we have A is equal to Ky because of this. So when you open this bracket, Kx0 and Mg cancel out, and A is opposite in direction. d2y by dt square. The same thing will apply for the second diagram also. We have Kx minus Mg is equal to Ma. But y is a negative quantity. So on either side of equilibrium, Yes, just got disconnected. Okay. So if y is the displacement from the mean position, then you can see that y will be doing this kind of behavior. E is sine omega t plus phi. So the extension of the spring it is equal to x naught minus y in general. So that will have this kind of a behavior. So whatever the amplitude of the SHM, accordingly, the extension of the spring will have a minimum value of x naught minus a and a maximum value of x naught plus a. And if that minimum value is negative, that means it's in fact getting compressed. So this is the extension of the spring, whereas this is the SHM parameter. So remember, y is the displacement from mean position, because we have taken our mean position as y equal to 0. It is not the net compression or extension of the spring. I'll explain that. In the second case, Jagannath, I'll explain that also. So in the second case, we've taken it from the mean position. We've taken it in the downward direction through a displacement of y. So our y coordinate is a negative quantity. Yeah, this case only, na? Yeah, so see, the y coordinate is negative because our y axis is upwards. You understanding? Na? So which force dominates now? The spring force dominates now. So kx minus mg is equal to ma. So in this we will substitute x as x naught minus y. Keeping in mind that of course y is a negative quantity here, but a will become d2y by dt square. So see the direction of a is along the positive y axis. So getting now the equation will become d2y by dt square. Yeah, exactly. A is positive of d2y by dt square because y axis is pointing upwards and a is also pointing upwards. So again, you get d2y by dt square is minus k by m. Yeah. There is a small correction here. It should be minus y here, but A is basically plus d2y by dt square. Like I've written in the thing below. This is minus y only. Sorry, minus mg, of course. But in this equation now, in the second diagram, you can see that A is in the positive direction. So it is plus d2y by dt square. But y itself is a negative quantity. So you can see that this quantity actually dominates over mg. So anyhow, so we have A is equal to minus k by m into y, where now actually y is a negative quantity, so A is positive. So d2y by dt square. Okay, so hope this is clear. The vertical spring mass system. So let's just quickly understand with one example. Okay, we'll just go through the example, then come back to the upper part, Jagannath. Okay. So we have a spring mass system with the mass of the block as, let's say, 5 kilograms and the spring constant as 20 newtons per centimeter. G is equal to 10 meters per second square. Now it is released from rest at t equal to 0 with the spring in relaxed state. So find time period and equation of its SHM x, that is extension of the spring as a function of time. Also we want to find. Okay, so let's look at this example. So in this example, what is happening is that t equal to 0, when we are releasing the system, x is 0. Okay, so immediately it has a downward acceleration and v is also 0. Okay. Now we need to compare this initial state with the equilibrium state. So the equilibrium state is actually somewhere below. Okay. So if this is the equilibrium state or mean position, here so kx naught is equal to mg. So x naught is equal to 20 divided by 5 or 4 centimeters. Okay. So now remember, we should take this as our origin for the SHM parameter. This position should be y equal to 0. So that means initially at t equal to 0, what is the y coordinate of the SHM? It is plus 4 centimeters because it is 4 centimeters above the mean position. Okay.
Sir, x naught
And
is
what is
mg
the
by sir x naught is mg by k.
yes?
Sir, so
Oh,
k
sorry.
value was
So
It will be
yeah.
3 by 20.
Sorry, my mistake. Okay, so mg by k will become how much now? 50 by 20 now. So 2.5. Correct?
yes,
Centimeters. Okay.
yes sir.
So okay. So initially, what is my position? It is at plus 2.5 centimeters. Okay. Because it's above the mean position by so much. And V naught is 0 because it's starting from rest. Okay. So now by applying the formula, omega is root k by m. So omega is square root of 20 into 10 raised power 2 divided by 5. So it's 20 radians per second. But what about these things? Now from this, y is some amplitude into sine omega t plus 5. So the velocity is a omega into cos omega t plus 5. Now applying the initial conditions, we'll get the value of amplitude and phase constant. So y naught, which is a sine phi, is plus 2.5 centimeters, and v naught, which is a omega cos phi, is 0. So amplitude is 2.5 centimeters, and phase constant is in this case plus pi by 2, because sine is positive and cos is 0. Okay. So from that we are getting our equation of SHM as y is equal to 2.5 sine of 20t plus pi by 2, or y is equal to 2.5 cos 20t. This is my y as a function of time. Now what is the position of the spring? X is equal to how much? It is x naught minus y naught, extension of the spring. So x as a function of time is actually 2.5 into 1 minus cos omega t. So you can see that at t equal to 0, x is 0. At t equal to capital T by 2, x becomes 5 centimeters. That is the maximum. This is the minimum. So the spring, oscillates between a state of natural length to 5 centimeters. Lowest position is where it's extended by 5. Highest position is where it started from at the natural length. Whereas the SHM parameter is such that the midpoint of that highest and lowest point is my origin. So it's ranging between plus 2.5 above and minus 2.5 below. So this is the important thing here, the difference between the SHM parameter and the spring state in the vertical spring mass system. Okay, so people, hope this is clear. With this, we'll conclude today's session.
Thank you, sir.
Thank you, sir. Bye, sir.
Yeah.
Bye, sir. Thank you,
So
sir.
there are a lot of there are a lot of spring mass problems in HC Verma exercise. You will see both vertical as well as horizontal, and there is like a variation or two where on a inclined plane, smooth inclined plane, there is a spring mass system. So it's very simple, similar to the vertical one, but this thing there, instead of mg, you have mg sine theta acting against the spring. Yeah, Jagannath, what is the question? X would be 2.5 centimeter initially. No, beta, because initially we are releasing the spring from the natural length state. Na? So the initial value of x is 0. That is why the initial value of y naught is plus 2.5.
Sir, can you also send today's notes?
Yes, I'll send the notes. Okay, so hope this is clear, Jagannath. Okay. Okay, so that's it, people. Thanks for attending.
Thank you, sir.
Thank you, sir.